So, how do we go about doing it? So, now we are going to use an iterative method. Okay. So, we are going to use an iterative method, and actually this is also inspired by clustering and all. So, this idea of mixture of Gaussians came from vector quantization and all these ideas and so on. So, k-means, and you will see that there is a lot of relationship between whatever we do there and what we do here. Okay. We use an iterative approach. Okay. What do we do? Okay. We randomly initialize these values. Okay. First, we randomly initialize we can do it more intelligently, right, the initialization, but let us for the time being. So, we have W1, mu1, sigma 1, W2, mu2, sigma 2. Of course, remember W is the proportion. So, W1, see if you see here W1 and W2 always have to add up to 1. Okay. In the labeled case, it is very obvious why it has to be 1, right. So, and there is a constraint that W1 plus W2 should be always equal to 1 constraint. This is a constraint. Okay. So, now if I do that, so remember my density function was a mixture of 2 Gaussians, right. So, mu 1 sigma 1 plus W2 into x mu 2 sigma 2, right. So, now we have all of the parameters available. Okay. This is essentially saying exactly what we discussed before of the labeled case. This is exactly like the labeled case. What I had to do in the labeled case? If you remember the labeled case, I had access to measurements from with their labels. So, I know which all measurements came from children, and therefore, I could find out the mu c and sigma c, where of course, this W1 is given by. So, once I know the measurements, I can count the number of children are there, count the number of parents that are there, the mean is given, and standard deviation also. If you go back in the previous lecture, there is, it will be this estimate that I get. So, this is actually an estimate, I should say. That you will subtract from xi the measurement and then square it and do it. Okay. And so, I will not bother about that for the time being. Okay. And so, this is a trivial problem, right. Once I got all of this, then I plug it into this original formula, right, this formula. That is all I had to do, right. So, if I knew, then I had idea of what the mixture for Gaussian was, what the mixture for parent, what the Gaussian for child was, what the Gaussian for adult was, and I also know the relative proportion of children and parents, right. Now, I have complete description for the children density function. I have the complete description for the parent, right. Similarly, here also I can look at these two. I can say one of this belongs, this is random, I have randomly initialized, but still I can say one of them belongs to child and one of them belongs to parent. Okay. That is what I am going to do. Okay. And I have randomly initialized this case. So, they might be arbitrary values, mu might be at some 5 feet 6 inches and mu 2 can be at 6 feet. I mean, we always, if you initialize reasonably well, right, I mean with reasonable making sense, right, in the real world, then your iterations will come out to a better answer. Okay, you will get a better value. So, normally we use some physics and intuition about the problem, or common sense, basically what these parameters should be, right. They cannot be negative, we know heights are never negative. So, all these things we put some prior information and put some intelligence into the random initialization. Okay. But let us say I have done this. So, I know that there are two populations and I have just randomly initialized. Now, I can think of this is that every measurement that I got, right, I did not have labels. So, why at this point we are assuming no labels are available, right. So, there was no label available, right. So, I had no labels, right. So, 2 feet 8 inches, 2 feet 3 inches, 5 feet 1 inch, 5 feet 8 inches, 5 feet 9 inches, 3 feet 1 inch, 2 feet 11 inches. Here that information label is missing, right? Now, with this random initialization, I have some guess which may be wrong or which may be right of the two populations. So, this is supposed to be a random, I mean with the random initialization, this is my guess of the density function for children, and this is my guess for the density function for the adults, right, or parents, right. So, this is what I have done here before itself, right. So, I found this easily, and then I said if I have the labels I can fit it like this, right. Now, all that I have to do is go back to my unlabeled data, okay, and ask. So, let me say this is, does it do it like a pattern, go back to the height measure. So, for each height measurement, so now this is like a two class problem. I am given a height, right, binary classification. I have some idea of the density function for n1 and some idea of the density function, because all these parameters are guessed, right. I have guessed it and put it there. So, now it is completely described, and does it belong to n1. So, I will look at, let us say this height n1, n1 h1, if it is greater than n2 h1, then assign to n1 class 1, right. So, I will put it to class 1, else class 2. Okay. So, by this way what will happen is, now I am providing some kind of a class, right, which I am guessing, I mean from the initial guess I have now tried to partition it into two classes, okay, based on this initial guess, right. Therefore, my population now will start getting some labels. They may be wrong labels, some of them can be completely wrong. So, I will get 2 feet 8, that might be categorized as class 1, 2 feet 3 might get class 2, okay. Then 5 feet 1 might again become class 1, 5 feet 8 might become class 2, 5 feet 9 can become class 2, and again 3 feet 1 can become class 2, and 2 feet 1 can become class 1, okay. But now this is got from this initial model that I had, which was randomly initialized, okay. Now, this looks like a label data, right. So, now with these pseudo labels, I get a number of counts. So, actually this normal and NC are coming both same, number of category 1, C1, and let me call that as NC1, right, that is the count for category C1, and similarly I can get count for C2, this is the count for category 2, okay. And then I can also find out all this, right, mu 1 and sigma 1, but this will be updated now. This is the new value, right, this is a new, this is new updated, right, and similarly mu 2, this is a new, and sigma 2 new, which these are updated using category information found in step 2. Now, I have an updated parameter f(x) of x, which is, now let me call this as W1 new N1 x mu1 new sigma 1 new plus W2 new N2 x mu2 new sigma 2 new. This is my updated value of this. Now, with this I can repeat, go back to and keep doing it. So, iterate until convergence, okay. Iterate these two steps until convergence. And there are some powerful ideas. So, you will be increasing what is called the likelihood. So, you will get at least to a local optimal values. Okay. So, this is called the more, if you look at the max this thing, this is basically the idea of expectation maximization or EM algorithm. Okay. So, this is well grounded maths is there. Okay. So, we will not go into the details, but this is a basic idea. Okay. So, if I know, if I did not have the category information, what can I do? I just randomly assume two categories, okay, put some values, initial values to them, mean, variance, whatever it is. And now that I have the two classes, the training data itself, I go back, which did not have any labels initially. I now try to guess the labels. So, I guess the labels. Now, because of the guessed labels, I get a new partitioning of the two population, right, the children this, and we iterate. Fortunately, it always will improve the likelihood that much. This algorithm will guarantee, and you will get to a reasonably good answer. Most of the time, it will work out very well. So, practically in many applications we do this. This is the basic idea of Gaussian mixture. So, if I can do it for 2, I can fit, I can fit for example, I might have a distribution, right. If I am looking at some arbitrary distribution, I can have some distribution that looks like this. Okay. So, we know that the total area of this should add up to 1. So, we can extend this idea to multiple Gaussians. Okay. So, if we are having a mixture of Gaussians, not necessarily 2, but multiple, let us say mixture of 16 or mixture of 8, right. So, why will such cases arise? Let us say I have a distribution and I did my histogram analysis like the table, right. The table looks something like this. Okay. Now, the tabular form had, if I had these measurements, right, if I made tens of thousands of measurement, I got something like this. Okay. So, some measurements like this I obtained, not necessarily height, we are going to do this for many problems, maybe cholesterol level, something, right. I was measuring the, sugar levels for diabetes, or I do not know, whatever, right, or the heart rates, when of different people, because of the, being athletes, many of them being heart conditions, whatever it is. So, I took a huge population, and it turns out my table looks funny like this. So many ups and downs are there, right. Now, how do I model this guy, right? If it is one dimension, it's sort of easy to see, right. So, I can see that there is a peak here, and so again, if it's one dimension, I can visualize there's a peak here, there's a peak, some sort of a jump here, there's a peak here, there's a peak here, there's a peak here, and so on. So, what I can do is now approximate this or model this now this table by having multiple Gaussians. So, I could say now fx of x is I can say there are 8 Gaussians here or something, right. So, it will be W1 n1 x mu1 sigma 1 plus w2 n2 x mu2 sigma 2 and so on all the way up to w8. So, this is a mixture of 8 Gaussians, okay. Mixture of 8 Gaussians, right. And then remember I have histogram here and there is no category kind of thing, right. So, we can fake this as saying this is one category of people or measurements, another category of measurements and so on, but this is real data, right. It's got many ups and downs. It so happens naturally this data is occurring in the way that I am showing, and so I want to fit a nice curve. Now, of course, there will be 8 into 3, 24 parameters, right, 8 into 3, 24 parameters, but nevertheless that is much better than this carrying this huge table, right, and you know, and to make sense of the table is also very difficult, right. I cannot just take the average and standard deviation, that is like fitting a single Gaussian, right, and that is not a good thing to do. So, this will describe the data much better form, in a much better way, and also it is very efficient. It uses only about 24 parameters and you get a fairly good you know function that describes this table of values, right. Again, we can think of this as belonging to 8 different subclasses or categories. So, what do we do? So, how do we estimate these parameters? Same idea, right. So, first we randomly initialize it, right, and so now it is like you know, each one of these Gaussian is matching some section of the population or section of the data, some I do not know, whatever it could be, the heart patient versus, I mean, I do not know, athletes. We do not need to have actually matching to physical thing, we may or may not, right, depends on how, what data we are looking at, what can we make sense of it. But the more we can explain the data, obviously it is better, right, to the real world, but often we may not be able to explain. But then we do what? Second step is we assign these pseudo labels to each of the measurement, right, or for pseudo labels that is one among the 8, right, if I am talking about 8 Gaussians, right, to each of these measurements. That is called hard assignment, okay, and there is also something called a probabilistic way of doing it. So, these are nitty-gritty details, do not worry, but the basic idea is I will choose one among the 8, right, and now once I have that 8 measurements, right, I now have divided this into 8 categories, right. So, divide all measurements into 8 categories. And then you know, update the parameters, right, update the parameters, right, with so so now I have divided, now I can, that updating of parameters happens the third step, right. So, once you know, with category information and that is how I am going to update the parameter, right. So, now I will get a updated f new I will get, right, because it will be w1 new what else, n1 x mu1 new sigma 1 new plus all the way up to w8 new and so on, and then I will repeat the step again, okay. So, I can generalize it not only for 2 Gaussian, I can generalize for 18, 8, 18, 16, whatever you want, 32, whatever you want, and if I can do it for one variable, I can do it for multiple variables, right. So, I can also extend it to multivariate Gaussian. What is that? If you remember, if I talked about heights and weights, that was a mu which was you know, x1, x2 kind of thing, and covariance or sigma which was sigma 1 1, sigma mu 1, sorry, mu 1 and mu 2, and sigma 1 2, sigma 2 1, sigma 2 2. This is bivariate, right? And then you can have multivariate as more dimensions, trivariate, multivariate, extend multivariate mixture of Gaussians, right? So we can do that also. So so once you get an idea of how to do it for a single variable, you can do it for multiple variables also, right? The same idea will continue, right? There, of course, it will be mixture of many multivariate Gaussians. Okay, this is basically what we call as a mixture of Gaussians. Now I will just we have already dealt with it, but I will just go through it in a little more detail. So what was it, the first thing we said, that first of all, it's better to fit one curve, two Gaussians if the data is having multiple modes, right, multiple peaks, right. So instead of fitting one Gaussian, that's not a good idea, right. And then the question is, if I fit this Gaussians, if I knew the category information, which is very trivial, right, if I knew that this data belongs to children and this data belongs, so if I have two Gaussians, I can take all of this guy, fit some data to it, get the means, and then take all this data and get the means. That is, if I know if it's child versus parent, right. If I do not know that, then what we do is we have to do some kind of, so we do not have labels now, right. So that is the problem, we do not know which measurement came from parent, which measurement came from children. So if this information about the category or the label is not there for each height measurement, then things become a little more difficult, right. So the first case we already have dealt it, I am repeating it. If I know the class labels, it is very trivial. I assign, I take all the measurements that belong to child. Once I have the measurements, I can find its mean and variance, right, and the proportion of children in that population. Once I have all the male measurements, I can measure and fit the male Gaussian. This is like a female Gaussian, this is like a children Gaussian. So these are very, very trivial if I have the category information, right. But if I don't, and this is the proportion that you are talking about, right, 4 out of the 12, there are 12 measurements, 4 of them belong to children. So therefore 4 by 12 is the W1, the weight that I was talking about. Here it's indicated as pi 1. Similarly, the number of females are 5 out of 12 and the number of males are 3 out of 12. So W1, W2, W3, they all have to add up to 1. That's the only constraint, right. And means are very trivial. Just take the heights of the 4 children, divide by 4. This is the height for the first Gaussian, the children Gaussian. This is the height. The second one is the height for the mean height for the for the second Gaussian, which is the female Gaussian. The third Gaussian, that mean belongs to the male heights, right. And similarly, we can compute this thing. But when we do not have the category information, we do not have this information, it is hidden from you, right. So we do not have the category information, then what we do is we try to predict. First we have to randomly initialize. Once you randomly initialize, you have 3, in this case let us say we have done only for 3 cases, we have all the 3 Gaussians. Then we ask, does the new data, this x1 data, the new the measurement that I had, does it belong to the first category or second category or third category, right. So that is what we are going to find out here. This is called the category information. So Z1, does it belong to the first category, or J is going to change from there. If there are 3 categories, J can be 1. So we are going to, this operation here is looking very complicated math. It is just trying to find out, does this x1 belong to the first mixture or second mixture or third mixture. We have now taken only 3 mixtures, right. So we have assumed a 3 mixture model. So we are asking a simple question, given that x1 is a measurement, does it belong to the first mixture, second mixture or third mixture. So for each one of them, so this is like a posterior, I have observed the data, right. How likely is it that it comes from category 1 or category 2 or category 3. So I compute for all the 3 categories, whichever is the maximum. So I do that for all the 3 categories, or 3, because I am talking about 3 mixtures here, whichever is the maximum, I am going to take that, right. Now I am assigning x1 to the label which has the maximum probability that that is the one that generated this particular most likely to have generated this particular observation. Okay. So this is a hard allocation. Sometimes we retain it with a weighted soft, which means probabilistic. If see if something is 0.4, 0.35 and how much is whatever is 0.35 whatever is remaining value for 1, the 0.4 gets all of this. So sometimes we take a weighted 0.4 goes to the first category, 0.35 to the second Gaussian, and 0.25 to the third Gaussian kind of thing. Okay. So those are nitty-gritty details, don't worry, and then you can easily work out the updated means and variance and we iterate it. This is basically nothing but the expectation maximization algorithm. Okay.